Good afternoon, everyone. I am Jan Rolig V. Conducto, together with my group mates, Jan Lester Santos, Gian Nicole Villamayor, and Jessica De La Cruz. We'll be reporting our final project revolving around a certain invention by humanity. But before we go into that, let me first introduce to you to a certain anime, Dr. Stone. For context, here is Senku, the main character. He is an intelligent man who is bringing the inventions right now into a Stone Age world in the future. So here is a reaction from one of those Stone Age people. It's a living iron creature built from nothing. And guess what? This is what she is talking about. Wooden wheels, wooden gears. Then Senkuan is a type of engine that is built from woods and stones. Literally a machine in the Stone Age. So once it runs, na-remind sila ng isang mahalagang invention ng humanity, the Industrial Revolution. When the engines were invented back in the 90s, it was the hallmark of the Industrial Revolution. And now we will be discussing a certain invention that is like this steam engine, but on a whole new level. It hasn't started a new evolution yet, but for sure it will in the future. So, what's our topic for today? We have magnetic levitation or maglev. So for context, magnetic levitation is just like this picture. It involves the concept of magnetism or electromagnetism in order to make certain objects float. So maglev has different applications. So in order for us to discuss what makes up a maglev and how it works, we've chosen to pick one of the most common application of maglev, which is the maglev train. So magnetic levitation is when it is used in maglev trains, its definition is a floating vehicle for land transportation that is supported either by electromagnetic attraction or repulsion. So dalawa agad yung pwedeng method dito sa pag nagamit tayo ng maglev train, and we will discuss both of it later. And for second, it mainly runs via the concept of electromagnetism, with its main characteristics being levitation, super fast speed, and being an environmentally friendly technology. We'll discuss all of that later. So for the table of contents, we've gone through the introduction. Next is the history, science behind it, advantages and disadvantages, and conclusion. For the history, Lester?
So for the history, in 1904, the famed American rocket scientist Robert Goddard, while still in a college freshman, made the first known breakthrough conceptualizing maglev. In a paper, he proposed a frictionless form of travel by raising train cars off the rails by electromagnetic repulsion roadbeds. In 1912, the French engineer Émile Bachelet applied for a patent on a rail car, which for purposes of levitation would use alternating current electromagnets, and for purposes of propulsion would use solenoids at intervals along the roadbed. In 1984, the first commercial maglev came on the line in Birmingham, England. In 1989, Germany constructed a maglev in Berlin that began operation in 1991 to overcome a gap in the city's public transportation system caused by the Berlin Wall. In 2001, 6 commercial maglev systems are currently in operation around the world. 1 located in Japan, 2 in South Korea, and 3 in China. So next. So here is some current maglev trains in the world. The first one is from Chu Shinkansen, Tokyo, Japan. In addition to being the oldest, the Tokaido is also one of the most heavily used. According to the Japanese government, the Chu Shinkansen has begun its construction to ease congestion that will eventually connect Tokyo and Osaka. Next. So the Incheon Airport maglev in Incheon, South Korea. The Incheon Airport maglev is a maglev line in South Korea opened on February 3, 2016. It is the world's second commercially operating unmanned urban maglev line after Japan's Linimo. Next. The Shanghai maglev train. The Shanghai maglev train is the first commercial maglev line in the world. In 2003, it was enrolled by the Guinness Records to be the fastest train in the world in commercial use. The last one is in the MagLev in Qingdao, China. China's introduced a high-speed MagLev train that can operate at a top speed of 600 kilometers per hour in Qingdao, Shandong province.
As you can see, maglev or maglev trains are a pretty new, maybe pretty new topic for most of the people, but it is actually in use na in different parts of the world right now. So in this part, we'll differentiate the two types of maglev trains, the EMS versus EDS, and we'll see how those two different trains use the concept of electromagnetism in order to run. So first we have the EDS.
So before we proceed to the first type of maglev train, let us first review what is electromagnetism. So electromagnetism is a process where a magnetic field is created by introducing a current in the conductor. So as we can see in the first picture or the upper picture, the direction of the magnetic field is moving from North Pole towards the South Pole. So the polarity of the electromagnet depends on the direction of the magnetic pole, of the magnetic field. And this magnetic field depends on the direction of the current flow. As we can see in the second picture, we can use the curl right hand rule to determine the direction of magnetic field that is created by the current. So if the direction of the current is upward, the direction of the magnetic field is counterclockwise. So if we reverse the direction of the current, the direction of the magnetic field will also be reversed. So that is why the polarity of the electromagnet can be reversed by changing the direction of the current. So going to the first type of maglev train, we have the electromagnetic suspension or EMS. So EMS incorporates the attractive forces between magnets to induce levitation. A stationary ferromagnet is placed on the underside of the rails. So we can see, as we can see in the picture, there is a magnet attached to the guidance rail. So that is the ferromagnet. So this ferromagnet attracts the levitation electromagnet, which is placed on the undercarriage. So this attraction creates a upward force which prevents the train to fall off. And this attraction also results in a distance of 10 millimeters between the ferromagnet and the electromagnet, and allows the train to hover 150 millimeters above the top of the guidance rail. So as we can also see a guidance electromagnet on the sides of the train. So this electromagnet keep the train centered over the guideway. So this prevents the train to move from left to right continuously or too much. So next. So for the lateral propulsion of mechanism of this train, so as earlier we said that the polarity can be changed by changing the direction of the current. So this concept will be used for the propulsion of the train. So the support magnet is responsible for the lateral propulsion by providing alternating current to create a series of attractive and repelling forces resulting in a forward motion. So as we can see in the picture, the north pole of the electromagnet repels the north pole of the ferromagnet that is placed on the train, and the south pole of the electromagnet attracts the north pole. So the repelling and attractive forces of these magnets makes the train move forward. So the direction of the electromagnet must be changed fast enough so that the train will continuously move forward. So it has to be fast enough so that the forward movement can be sustained.
So that's it for the first type of MagLev train, the electromagnetic suspension. Now we'll move on to the second type, which is electrodynamic suspension. So in electrodynamic suspension, we have the same characteristics. We have levitation, and we bought yung isang significant characteristics is this type of train become the fastest train na na-record sa Guinness. And it is also called as SC maglev or superconducting magnetic levitation because the heart of this kind of train is the superconducting magnets shown right here. So let me first discuss what this is. So this is the SC maglev, the superconducting magnetic levitation. So bali itong mahabang rectangle ito is the for 1, 2, 3, 4, 2 pairs of superconducting magnets na instead of electricity yung nagiging source of energy ng train, ito sila yung nagbibigay ng energy dun sa train. So itong types ng train na to, meron din silang 3 characteristics tulad nung sa EMS kanina. They need to propel, they need to levitate, and they need guidance para hindi sila maaksidente. So, as Jessica discussed earlier, she already gave the introduction about electromagnets. So, yung power na itong electromagnet na to, ito yung nagbibigay ng energy towards the whole train. But ang problem kasi nito, if masyado nang gamit siya, tataas yung temperature, iinit, masisira yung electromagnet na to. That's why gumagamit ng supermagnets, itong EDS natin. Ang ginawa naman nila dito, ibinaba nila yung critical temperature ng magnet. Tapos mababa sa critical temperature, kung saan almost zero na yung resistance para kahit anong ikot ng current dito is hindi tataas yung temperature, hindi sila masisira. However, initially lang yan. Initially lang na hindi masisira yan. At some point, may pwede pa rin tumaas sa critical temperature yung level ng temperature sa loob ng magnet. Kaya meron pang ibang nilalagay dito. We have the liquid helium na kung saan magpapalamig dito sa mismong supermagnet natin. And then yung lalabas na helium dito, helium compressor, babalik dito. Papalamig na yung mismong magnet. But kahit na malamig na yung mismong magnet, meron pa rin init mula sa outside sources na pwedeng pumasok doon, so hindi pa rin solve yung issue. That's why meron din silang radiation shield para maalis yung outside sources of heat. But since wala na nga outside sources of heat and malamig na yung mismong magnet, ang last na problem na lang is yung init mismo sa loob ng box. That's why meron pang another chemical which is the liquid nitrogen para mapalamig naman yung inside ng box. And then there's also, as you can see, yung boxes hindi sila nakadikit dun sa magnet para hindi magkaroon ng convection. So wala na talagang init na papasok dun sa magnet. Magkatuloy-tuloy na lang sila. So this is the heart of every EDS train na makita dito sa Earth. Bali, itong isang solid na itong rectangle, meron silang dalawang pair ng superconductive magnets, north-south, north-south. And this will be the one running the train. But that's just the basic. Now we'll discuss how the train achieves its 3 characteristics, which is the propel, the levitate, and the guidance part. So for propulsion, katulad lang siya nung sa EMS kanina, we have the propelling coils dito sa gilid na kung saan north-south, north-south, north-south. So pag makita niyo dito, north to north, so i-repel niya papunta pa forward doon, tapos attract dito. But pagka-attract dito, ang gagawin is mag-switch naman yung and pagka-forward dyan, biglang mag-switch. So yung unang na-attract sa kanya is magiging repel din siya. Balik forward na forward. Katulad lang din nung sa EMS kanina. And mas mabilis yung pag-alternate ng north-south, north-south. Mas bibilis din yung pag-propel nung train natin. So as you can see, through electromagnetism, or magnetism pa lang in this point, kaya nang propel ng train natin at great speeds. Tulad ng pinakita ko kanina, umabot siya ng about 600 kilometers per hour. Next will be the levitation. This is the key characteristics of MagLev kasi di ba magnetic levitation. So how can we use magnets to levitate? So sa EMS kanina, makikita nyo is, di ba sa EMS kanina, merong magnet dito sa rail, tapos meron ding magnet dun sa train mismo. Bali yun yung nagpapaangat sa kanila. Ang difference dito sa EDS, yung magnet is wala sa ilalim at taas, nandito siya sa gilid, at nandito sa railways mismo. So let's discuss paano yun nangyayari. So makita niyo yung railway dito, ito yung key dito, meron tayong nakabaliktot or H-shape na coil dito sa gilid. And doon naman sa loob, yung pinakita ko kaninang heart of the train, yung superconducting magnets natin, since meron silang isa sa left, isa sa right, nagsasama na yung force nila at parang ganito. To better represent the train, we'll imagine a big magnetic bar with north and south pole here. So as the train moves forward, kapag nasa gitna siya initially, same yung force dito sa baba and sa taas ng ng railways natin. So wala masyadong magganap. However, that's not reality. In reality, yung train sa atin is initially nasa baba. Hindi naman siya laging nakalipad. So pag nasa baba siya, yung force dito sa baba and force sa taas is magiging unequal. So mas malaki yung dito sa baba. Then magkakaroon siya ng bigla ng induced current. So paano siya nagkaroon ng induced current? So i-apply natin yung mga tinuro ni Sir Nate, ni Sir Levitation, and let's go back a bit. So di ba makita niyo dito meron tayong uneven forces dito. And kapag in-expand natin yan, kapag binuka natin to, magiging ganito to. Yung nasa taas is pa ganun, yung nasa baba is pa ganun. Paano ba siya nangyayari? So, next slide. Going to the next slide. Oops. So, oops. Yan. As you can see here, bigla nilang milalabas na electromagnetic field dyan. Yan yung nagkakos ng pag-levitate niya. To understand paano siya lumabas, ulit ibubuka natin yung coil natin dito. And as you can see, di ba nasa baba to, tapos tataas. So kapag gumagalaw yung magnet bar, tapos pumapasok siya dito, nagkakaroon ng change in magnetic field. And via Faraday's law, the change in magnetic field will have induced current. So the formula is induced current is equal to negative N times change in magnetic flux. Is that correct? That's over change in time. So, since nagkaroon tayo ng change in magnetic field, nagkaroon tayo ng change in magnetic flux, magkakaroon ng induced current. Pero paano naging ganun yung direction ng current? Gamitin naman natin si Lenz's law. Right here, this is the Faraday's law. And we have here the Lenz's law, which is connected din kay Faraday's law. As you can see, di ba, dito sa Faraday's law, we have the negative here. So that will be explained by the Lenz's law. Pag in-unwind natin itong 8 coil na to, meron tayong north na pumapasok dito. Ang magnetic field outside ng loop is going outside. But since nung pumasok yung magnet dito, lumakas yung magnetic field dito. Pag tumaas yung magnetic field, mag-increase yung magnetic flux and via Lenz's law, to achieve equilibrium, ang gagawin ng system is gusto niyang magbawas. So pag nagbawas siya, gagawin niya opposite yung direction ng magnetic field. So since dito is papalabas towards you, tapos dito papasok into the page, ang magiging direction ng ating magnetic field ay how to change color. Oops. Ganito siya. And katulad ng tinuro kanina ni Jessica via right hand rule, since papaganto yung pasok ng magnetic field, yung tab natin is towards pababa. So ito yung current natin ngayon. So pababa dito, papasok doon, papasok doon, papasok doon. Ang flow ng current natin dahil din sa via Lenz's law is clockwise. So as you can see here, in-unwind to pa ganun. Pasok siya doon. Ito, di ba, bababa ito. Ayan, bababa siya. Tapos gaganon. Eh, nagbalik ka dito kasi nga, tinwist natin yung itong box na to. And since papaganon siya, ito, Di ba, labas to, tapos ito pasok. Sabihin, ito yung north, ito yung south. So, nagkakaroon ng North Pole and South Pole na nandito. Kaya after nun, nagkakaroon ng yung from simple na bar lang kanina. Wait lang, let me clear my drawing. Yung simple na bars lang kanina is nagkakaroon bigla ng magnetic North Pole and South Pole. And since nagkaroon bigla ng lalabas dito, ayun pababa yung current, north to north, magkakaroon siya ng repulsion. Repel yung north doon, tataas yung tapos kasi ma-attract pa siya dito sa south. So from nasa baba, magkakaroon induced current, magkakaroon ng magnetic field, magkakaroon ng north and south pole, mare-repel tong north to north, ma-attract dun sa south, aangat na nangangat yung train natin. And pag nasa gitna na siya, na-equal na yung forces, nanatili na siya dun sa equilibrium na nakaangat siya sa gitna. So from bottom, bigla siyang lilipad through the use of the Faraday's and Lenz's law. So that's how MagLev trains attain levitation. So for the third one, the guidance, it also lies in this railway ulit. So as you can see, ang dito, hindi lang siya basta two railways, meron siyang connection sa ilalim. Kapag nasa gitna, again, equilibrium lang siya. But for example, ayan, no, current flow, if equilibrium lang siya. But for example, bigla na lang gumilid pa kanan yung magnet natin, magkakaroon ulit ng effect dito. So yung, pansinin nyo, north and south, almost same lang sila. Oh wait, dito almost same lang sila, pero pag dito, lumaki yung S compared dun sa N. So yung movement nitong S papalapit dito is nagkaroon ng induced current dito. And since connected sila, magkakaroon din ng current flow dito. And I could also explain bakit nag-gain direction, but it will be a little bit overkill. So for simplification, since nagkaroon ng current flow dito, yung magnetic field is magkakaroon naman ng bagong direction by Faraday's and Lenz's law. And then may higit pa balik sa gitna, yung big magnet natin, which is our train. Oops. Yan, gumita na siya. So, yun yung tatlong characteristics ng MagLev train, the propulsion, the levitation, and the guidance. Lahat ng yun is walang use ng electricity but pure electromagnetism. Next. But kanina, di ba, doon sa electromagnet, di ba, pag electromagnet, in order to make them work, we need to induce a certain electricity for that. So, wala man electricity mismo na nagpaparan dun sa propel, levitate, and guidance. Need na electricity sa initial part yung pag-spark ng superconducting magnets natin. And ang ginagawa yan, hindi siya nakasaksak but nasa ilalim ng railways, may tinatawag tayong inductive power collection na kung saan wala man siyang walang connection but via electromagnetic induction yung magkakaroon ng kuryente dun sa power collection coils na nasa loob ng train galing dun sa ground coils na nasa baba. And another one here is yung problem kasi meron tayong superconducting magnets. And dahil masyadong malakas yung magnetic field na yan, merong hinaharang na sheets dito para hindi maapektuhan yung mga tao. Ayan, so as a summary, sa EES, ang main source of power niya is yung superconducting magnets. And one trick dun is, based dun sa sources namin, isang beses lang talaga siya nag-spark and then it will continuously run all throughout the traveling. And bahala na yung concept ng electromagnetism para guide yung train throughout his biyahe. So, now, we'll present the advantages of disadvantages of using maglev trains. Gian?
Okay, so moving on to the advantages of maglev trains in comparison to our conventional trains. Firstly, next slide. Firstly, they are capable of reaching higher speeds. Well, as Ralik has mentioned kanina, this is because of the principle of electromagnetic propulsion. Well, maglev trains do not really have engines because they move based on this principle. So maglev trains, they move with the help of electromagnetic field created by electrified coils in tracks or guideway walls. Thus, the charge alternates constantly, and this change in the polarity causes the magnetic field in the front of the train to move it forward, whereas at the back, the magnetic thrust pushes it forward as well. And well, the basic idea here is, or the basic idea in behind the form of electromagnetic transportation is one, to have a huge power source, and two, to have metal coils lining the track or guideway, and lastly, to have large guidance magnets attached to the train's underside. So next. MagLev trains have a strong magnetic field. As mentioned a while ago, the term MagLev is derived from magnetic levitation. When the train moves, the magnetic field repels the magnets, causing the trains to levitate. So these trains produce magnetic fields that are up to 10 times stronger than typical electromagnets, which are powerful enough to suspend and move them. It then results to next. It then results to the elimination of the key source of friction. Since we know that friction is what causes the objects to resist one another, there will be no force that will slow these trains down. So lack of friction means that they can reach higher speeds than conventional trains. And then, as we have researched, maglev trains can travel in excess of 300 miles per hour. In the present, their speed is twice as fast as conventional commuter trains and comparable to TGV or the Dragon Vitesse, a high-speed train used in France, which travels between 186 to 199 miles per hour. And then next slide. Another advantage is that it is less expensive to operate and maintain. Well, they are less expensive to operate and maintain because of the absence of rolling friction, which means that its parts do not wear out quickly. For instance, in comparison to a conventional train, the wheels, I just mentioned a while ago that there is no friction involved in maglev trains. And then next. This means that the train consumes fewer materials because parts do not have to be changed on a regular basis, and thus it does not have to be maintained constantly. Then lastly, maglev trains are eco-friendly. Maglevs produce little to no air pollution during operation since no fuel is burned. These trains do not use fossil fuels mainly because, like what I've said while ago then, they do not have any type of engine, making use only of magnetic field force to move. And then, in addition, noise pollution is much lower than in traditional rail. The absence of friction makes the trains very quiet and provides a very smooth ride for the passengers. So to summarize, maglev trains are faster, more efficient, and definitely more eco-friendly than the usual trains we travel on. The next slide. Of course, there is no such thing as perfection. So these maglev trains have also this disadvantages. Oh, okay, so high initial cost. You might be confused because I've mentioned a while ago that one advantage of maglev trains is that in terms of cost efficiency, it is less expensive. Well, to be more specific, it is less expensive in terms of the operation and maintenance. So the greatest obstacle to the development of maglev systems is that it is not compatible with railroad track, and thus it required routes to be built from and it required the entire route to be built from the scratch. So with this, they require entirely new infrastructure that cannot be built or integrated with existing railroads, and that would also compete with existing railways, railroads, and air routes. And next. Actually, maglev guide paths are more costly than conventional steel railway because the maglev coils and materials used in this setup are very expensive. Maglev trains require an all-new setup right from the scratch, so it requires so much work as well. And then, lastly, another factor to be considered in developing maglev rail systems is that they require the use of rare earth elements such as scandium, yttrium, and lanthanides, which may be quite expensive to recover and refine. But magnets from rare earth elements, however, produce a stronger magnetic field than ferrite or alnico, which is used to lift or guide the train cars over guideway.
So, we've already discussed the two types of maglev trains, the electromagnetic suspension and the electrodynamic suspension. They seem to be good as they provide new technology such as super fast speed, and then as Gian mentioned, there's a lot of advantages, but there's also some disadvantages. However, there's been current developments, and there's a third type that is being done, and it will be discussed by Lester.
Next. So the third type of the current developments of the maglev is in the Inductrack. So the Inductrack uses a special arrays of permanent magnets as a means of passive magnetic levitation for moving objects. So as the vehicle moves over the track, Inductrack magnets induce a current in the track circuitry. This current generates a magnetic field that repels the magnet arrays. So next. So here you can see the special arrays of the permanent magnets. This is called the Halbach array. A Halbach array is a special arrangement of the permanent magnet that augments the magnetic field on one side of the array while canceling the field to near zero on the other side. This is achieved by having a spatially rotating pattern of magnetization. So in simple words, the Halbach array helps to concentrate the magnetic field towards the levitation circuits and lessen the magnetic field towards the people or the train itself. So next. So here is some benefits of the Inductrack. First, it is cost effective. Further savings come continuously since electrodynamic maglev designs like Inductrack do not require powered feedback control systems to stabilize its levitation. 2. Inductrack is lighter with greater stability. Inductrack vehicles glide over track constructed with circuits that form a ladder-like array of rungs of cabled insulated wire. As the vehicle moves over the track, the Inductrack magnets induce a current in the track circuitry. This current generates a magnetic field that repels the magnet arrays. The result is levitation with greater inherent stability. Then the third one is it eliminates passenger screening. Due to the Halbach arrays where the magnetic field is concentrated toward the bottom rather than towards the passengers, it eliminates passenger screening because the designs of maglev trains are used to screen people with certain gadgets and accessories, as it may interfere with the magnetic field. And the last one is it is safer in the event of a power interruption. So it is safer in the event of the power interruption since the main power used in order to propel the train forwards is the soft spark and the induced EMFs.
So for the summary, conclusion, we've seen how maglevs are being applied in real life. So again, magnetic levitation is just a concept of how magnets can be used to levitate through entirely the use of electromagnetism. And one of its major application is the maglev trains. First, for us, maglevs provide a whole new level of possibilities because as you can see, maglevs can make trains fly, can make vehicles fly, and not just simply fly, but to move in in really fast speed. That's why we think that it will soon be the basis of transportation structure in the future. And as I mentioned earlier, it might be a spark plug for a certain type of revolution in the near future. And as Senko said, that's the way science is. Thank you for listening again. I am General Victor Ducto together with John Lester Santos, Eric Villamayor, and Jessica De La Cruz. Thank you for listening.